This is the second in the series of videos about phase transitions. In the last video, we talked about how puddles evaporate due to a process called vaporization. And now we're going to talk about boiling and how that's a little bit different, a different type of evaporation. So if boiling is not the same as vaporizing, what is boiling? So if we think about our coffee cup that we drew in the last video, where some of the molecules were warm enough, what would happen if we increase the temperature? We increase the temperature of that cup. So our Boltzmann distribution with the different kinetic energy speeds would shift towards higher energy, and it would flatten. So it would scoot over, and more of the molecules would have a higher energy at this point. The particles would have more kinetic energy because of that increase in temperature. And then with more kinetic energy, more of the particles would be able to escape to the gas phase. And the more particles we have in the gas phase, the higher the vapor pressure in the container with the lid on. So the vapor pressure increases. So if we continue that process, we continue to increase the temperature until the vapor pressure goes higher and higher and higher. Eventually, we hit boiling. We reach a temperature where that vapor pressure, due to the molecules becoming warm enough to jump into the gas phase, is equal to the pressure of the surroundings. Or you can call it the pressure of the atmosphere. And when those two are equal, we call that temperature where that happens the boiling point. So boiling is a type of vaporization that has specific pressure requirements. When we use the word or the phrase boiling point in everyday life, what we're really referring to is the normal boiling point. Normal boiling point is the temperature of boiling at room pressure, which is defined as 1 atmosphere. So the normal boiling point for water would be 100 degrees Celsius. That's the number that we use doing calculations, or 212 degrees Fahrenheit. So that's the normal boiling point. But this is new information, right? The boiling point of 100 degrees is only at this particular pressure. And so that means that the boiling point is pressure dependent. So we should think about what would happen to the boiling point if we change the pressure. So let's make a plot of what it would look like. So we're going to put temperature, boiling point temperature on the x-axis, and vaporization pressure on the y-axis. And if we draw the plot for water, our diagram is going to look like this. It's going to be a logarithmic curve that increases its slope as it moves forward. And if we're going to make our plot point for water, boiling at 100 degrees, it would be at 1 atmosphere. We could trace that over to this spot and drop it down to here. So this is going to be our normal boiling point of 100 degrees. And so what we see is that instead of a boiling point, like we've been told, 1 temperature pressure coordinate, it's instead a boiling line. It's a series of different temperature pressure combinations that water can boil at. So let's think about what might happen if we changed the pressure of the system and how the boiling point might change. So an example from your everyday life is a pressure cooker. Pressure cookers have a slightly higher pressure than normal pressure. It's about 1.02 atmospheres. And if we look at the boiling point under those conditions, here we are, there's our intersection with the line, and we drop it down. That boiling point is at 120 degrees Celsius. And this is an advantage because when you're cooking food, some food needs to be cooked at a higher temperature. It needs to be cooked at 100 degrees Celsius. But if I were to cook my food at 100 degrees Celsius in a normal pot, all of the water would boil off and there would be no water to use to cook the food. So with the pressure cooker, I can cook food at 100 degrees Celsius and it hasn't hit that boiling point transition line yet. So I can cook food at a higher temperature without losing all my water. Let's do an example the other way. For mountaineers climbing Mount Everest, if you go up near the top, you will experience very, very low pressure, 0.3 atmosphere. And the boiling point for water at that temperature, or at that pressure, is only 5 degrees Celsius. 5 degrees Celsius. That water is going to taste super cold. You can't cook anything in 5 degrees Celsius. So when you climb Mount Everest, you actually have to bring a pressure cooker to boil water with you because you won't be able to boil water and have warm food at that such low pressure. So these are real issues that you use in your everyday life. And so this logarithmic curve of the pressure of the vapor versus the boiling point has a name. And the equation that we use is the Clausius-Clapeyron Equation, named after two folks who modeled it. And the equation is the vapor pressure equals A times an exponential term, negative enthalpy of vaporization over R times T. So A is a constant, and it depends on the compound. You can look this up in a reference table. And then we know delta H of vaporization. We can find temperature and vapor pressure. And then look, it is our friend R, the gas constant. And we're going to add a note because we have the gas constant and enthalpy in the same term. We want to use a different set of R than we usually use. We want to use the one with joules in it, the 8.314 joules per mole Kelvin is the one we're going to pick for this section. This is our equation from the graph. So we can use this equation to relate the vapor pressure and the temperature, but you'll notice that this is not a linear relationship. This is logarithmic. And we really like to transfer equations into linear relationships in science because there's a lot of information we can really easily grab straight off the graph. We can grab the slope and the intercept. So we do whatever we can, we wave our magic wand to linearize. So we can wave our magic wand in this scenario to linearize the graph. And what I'm going to do is I'm going to take the log of this entire equation of this, because this is a logarithmic curve, and that will convert it into a linear relationship. So I'll take the natural log of both sides. So natural log of vaporization pressure. And then when I take the log of this term, it separates into two. Natural log of A plus natural log and exponential undo each other. So negative enthalpy of vaporization over RT comes out by itself. So now this is going to look like a familiar structure. If you squint, it looks like Y equals mx plus p. So in this form, we can really easily grab the slope of this equation, and we can really easily grab the intercept of the equation without even having to make the plot. So remember when we did the gas law chapter and we said, here's the ideal gas law in a usable form, and another more usable form is if we have two scenarios, if we can relate it. So we made a P1V1 equals P2V2. That's something we can do with this equation as well. Because we have a constant, we can set two different equations equal to the same constant and find a way of relating two scenarios together. So let's say we have two scenarios. So we're going to solve for this constant, natural log of A. So we can move both of these two terms to the left So we'll end up with natural log of P1 plus delta H vaporization, which is the same all the time, R, which is the same all the time, and T1. That's equal to natural log of A. And if I took the same equation in scenario 2, that would also be equal to natural log of A. So natural log of P2 plus delta H of vaporization over R times T2. And we can do the same thing as we did in the last chapter, where we set these two equal to each other, and then we're just going to rearrange it so that it looks a little bit nicer and group a few of the terms together. And when we do that, we end up with natural log of P2 over P1 equals the delta H of vaporization over R times 1 over T1 minus 1 over T2. And this is our most useful form of the Clausius-Clapeyron equation. So this isn't magic, this is just math rearrangement to make the equation more useful. And so let's do an example of using that equation if we know one set of boiling point temperature coordinates, and if we know the delta H of vaporization, we can solve for the boiling point at some other pressure without having to actually do the experiment. So let's say we've got benzene, which is C6H6. Let's say that we know the boiling point, the normal boiling point, which is 80.1 degrees Celsius, and we know the enthalpy of vaporization, which is 30.8 kilojoules per mole. So if we took that compound to somewhere with a different pressure, like Denver, and we know the atmospheric pressure is 83.4 kilopascals, we can solve for the temperature where it boils for that place. So let's break it down here and sort our variables. So we're going to have situation 1 and situation 2. And I'm going to label them right now so that I don't mix them up when I'm plugging them into that formula. All right, pressure for situation 1, it said it was at normal. Remember, the normal boiling point is at 1 atmosphere. So that's a key piece of information hidden in that word problem. So 1 atmosphere, and I can see that my other pressure unit is in kilopascals, so it would be helpful if they were in the same unit. So I'm going to go ahead and convert this one to the same unit. So it's going to be 101,325 pascals in 1 atmosphere and 1 kilopascal per 1,000 pascals. That should cancel pascals. Atmospheres will cancel. We get 101.3 kilopascals. When you're using this equation that has a fraction in it, it doesn't matter what unit you use, as long as the units are the same for pressure. All right, temperature 1, it said the normal boiling point was 80.1 degrees Celsius. And we are back in the land of familiar chemistry where we always have to convert to Kelvin. So we can add 273 to convert to Kelvin, and we'll get 353. All right, so that one is set. And then for our second situation, what is the temperature at this atmospheric pressure? So atmospheric pressure, 83.4 kilopascals. And we are looking for the other boiling point. All right, so we've found all the information we need. We've labeled it, we're ready to rock and roll. The way you can identify you're looking to use this form of Clausius-Clapeyron is because there's 2 situations and because you have the enthalpy of vaporization or you are looking for the enthalpy of vaporization. Okay, so here's our formula. We need a pressure ratio. We need the enthalpy of vaporization. And we need 2 temperatures. All right, so we'll go ahead and plug it in here. Make sure you keep track of which one is situation 1 and which one is situation 2, or you're going to get a very different answer. Okay, we plug in the pressures, vaporization, and if you're following along with your units, you'll notice we're going to run into a problem whenever we do this type of a problem with this equation. One of these numbers is going to be given in kilojoules and the other is going to be given in joules. So you want to make sure you convert one of them so that they're both in the same. So I'm going to choose to convert this top one. I'll multiply by 1,000. So they're both in joules. And then we'll do our temperature ratio. So T1, that one was 353 Kelvin. And we don't know T2. Okay, we're going to be putting our algebra skills to work when we do these problems. You're going to need to remember how to undo a logarithm and how to do the order of operations. So I'll do this one all the way out just to make sure we're all on the same page. So if we divide and we take the natural log, we multiply these numbers. And if we reduce that temperature fraction, coming along. So we do within the parentheses first, then we rearrange everything to the left side. We can isolate that parentheses with the variable we're looking for. Okay, then we want to isolate this term, so we'll move this one left and the rest of them right. And we take the inverse of both sides. So don't let the math trip you up. Okay, so we end up with 346.9 Kelvin, and I think that number will be more relatable in Celsius, so I'm going to do a quick conversion to 73.8 degrees Celsius. If we do our bullshit test, we see that at 1 atmosphere, we were at 80.1 degrees Celsius, and when we decrease the pressure, we decrease the temperature. So that is appropriate. That's how we expect our curve to look. Higher boiling points should happen at higher pressures, lower boiling points at lower pressures. And in the last video, we will talk about heating curves and some of the phase transitions between other phases other than liquid and gases.